Okay, so this is a key corollary from what we've been doing, and it's just to say that solution sets of linear systems are either empty, have one solution, or have infinitely many solutions, and these are the only three possibilities. So the way we do this is we use what we proved, which is that every single solution set of a linear system can be expressed as a particular solution plus the homogeneous solution. Now, the first thing that we should sort of see is that if we have a homogeneous system with, say, V as a non-zero solution, right? So it's not the zero vector. Then the system, the homogeneous system, the system we're talking about, the obviously the homogeneous system, has infinite solutions. And this should be obvious because if we have V as a non-zero solution, then C times V for any C contained in R, right, okay, is also a solution, okay? And that's easy because you know that V is a solution to, V is a solution to the ith row in the homogeneous system. So again, you have the ith row, right? And then you have some d sub I, and then now you know that this vector is a solution, so you have to the homogeneous system, sorry. Good. So you know that this is true, right? That V1 plus dot 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 En equals 0, right? Now, what do you need to show? You need to show that simultaneously C times, where C is non-zero, I should say. C doesn't equal 0. Well, it doesn't matter, but it's C is anything contained in R, and either way, you're going to get an infinite number. But here, then you're going to get A1I C times V1 plus dot 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 A1N C times Vn equals what? And then you want this to be also 0. Well, C can factor out, and then you should see that then you get that this is on the inside, right? And this, we know from here, is 0. So then this is C times 0, and you get 0. And indeed, this here is also a solution. And that was any C in R. There's infinitely many. Therefore, a homogeneous system with V as a non-zero solution, then the homogeneous system has infinitely many solutions. So there's also the case where a homogeneous system has one solution, which is the 0 vector. So there's two cases for the homogeneous system, right? It could either have one solution or infinitely many solutions. Now, what you say is you can say that this here, right, we know that the solution, right, we know that any solution to the system is in this set, right? H solves. From the lemma, we know that any solution to the system is of this form, is in this set, solves the homogeneous, right? Solves the homogeneous system. Okay. Now, you want to see that this set is either empty, has one member, or has infinitely many members based upon just this argument here. So we know that if there's no particular solution, then this set is empty. If there's no particular, right? So what are the cases? No particular, No particular, right? If there's no particular solution, then set is empty. Okay, now let's say there is a particular solution. Okay, then it goes to, okay, well, the homogeneous system can only have what? One or infinite solutions. So if there is a particular, right? Particular, then the homogeneous system has either one solution or infinite. The homogeneous. Okay, the homogeneous either has one solution or infinite solutions. If there is a particular. Now, if it has one solution, then it's the zero vector. And then ultimately you get that there's one solution, just the particular. Right? If there's one solution to the homogeneous, because then the homogeneous is zero and you get back to particular, because the particular plus the zero vector is just the particular, right? And then if you have infinitely many solutions, then it's the particular plus an infinite number of different possible solutions. So then you get an infinite number of solutions, and then that's it. Those are the only possible combinations, right? Either there is no particular or there is a particular, right? If there's no particular, then the solution set is empty. Okay, and we're done. Okay, because we can't put it in this form at all. Okay, now if there is a particular solution, at least one, say, I don't know, P, right? And then you look at the homogeneous, right? Now the homogeneous system either has one solution or infinitely many solutions based upon what we said here, right? We know that there's always at least one solution to the homogeneous system, which is the zero vector. If it is the zero vector, then it's the only solution, okay? Because you can't get more than that with the homogeneous system. Now, if there's a single non-zero vector, right, that is the solution of the homogeneous system, then we know we can multiply by any scalar to get another solution, or infinitely many solutions, because we can multiply by infinitely many scalars, and they'll all be a solution to the homogeneous system. So then this gives only the three possible combinations, and now you're done.